Yep.
Wonderful. Thank you so much, Anman, for the introduction and having me here. It's really such a pleasure to be joining you all. Um, I'll get started. Um, I'll be talking about broader ways of accounting for and mathematically addressing and overcoming uncertainty for decision making in environmental context. Hi, Cindy. So just a little bit of overview of some of the ways that decision making under uncertainty shows up in climate and sustainability applications. So when we have a lot of transmission lines or other forms of physical infrastructure, these will eventually degrade over time and require regular maintenance checks. But the point at which there be a degradation past a certain point where it's no longer functional or hazardous or disruptive to power generation happens in very stochastic noisy intervals, and many of these events will happen independently. So these types of maintenance checks requires us sending out people to inspect each form of transmission tower and performing any kinds of maintenance checks as necessary. But the challenge is that doing any kind of inspection is costly, so we want to make sure that we're sending people to the right places and then also collecting as much information as necessary as possible in order to um, better understand the kind of state of our physical infrastructure. If we have invasive animals that we're trying to address within our landscape, we need to consider how to best eradicate these invasive animals while there being a lot of dynamicism in terms of exactly where these species are present. So the emergence or movement of an invasive species to an area and then our removal of it might happen in various cycles. We require repeated interactions to remove these animals multiple times. So this example is of a Burmese python in Florida, which is hugely invasive. And we can also imagine for smart home users where their home is connected to a smart grid. Might want them to adopt specific practices like only using power at certain times when there's lower loads. So we can imagine that some users set up a schedule in which they'll automatically reduce the thermostat or turn on their dishwasher at night and reduce the consumption of these types of utilities during peak hours. But then at some point, maybe somebody really has to run their dishwasher at 6 p.m. or it's really, really cold in the morning, so they'll turn up their heating. So at some point, users might stochastically drop off the ideal timing schedule, and then we'll have to come back and remind the users to get back on the schedule that we desire. So across all of these broad various settings, there are several characteristics of these problem contexts that are shared. So all of these contexts require repeated interventions. So we repeatedly have to send a person to do some kind of action. And the more that we're able to intervene in a specific example, the more useful we know will be in that context. So we'll be more confident that a certain transmission tower is in a well-functioning state. We'll be more confident that a certain area is rid of invasive species. We'll be more confident that a specific individual is kind of optimizing their power usage. But we have very limited resources. So trying to figure out how to best allocate these limited resources across the large number of different things that we can intervene on is a key challenge. So we have decisions over large sets of individuals, and then us acting on one individual, like one user in a home, for example, or one transition tower, in many cases is independent. So we really have to make sure that we're best allocating our resources and focusing on the kind of like individuals of greatest impact or the places of greatest need. And as a result, we also have multiple processes evolving simultaneously. So the state of one transmission tower can degrade even without while others are still in good condition. And then us doing a repair on one transmission tower is not going to improve the state of other towers. So a framework that can help capture this types of problems is known as a restless multi-armed bandit. Um, and let me walk through what this means. So a restless bandit is a form of a coupled Markov decision process. So there are, we can model each individual unit in the setting. So we can model one smart home user, for example, as a Markov decision process where there is some state associated with this individual. So they can either be kind of engaging or not engaging with the power optimization program that we want them to enroll in. And there is some probability that they'll transition from the engaging state to the non-engaging state. So on any given day, there's some probability that they'll kind of turn off their schedule because of some conditions in their daily life where that need arises. And then if they're in that non-engaging state, there's some probability that they'll go back to enrolling in that schedule. And we can also intervene on them. So if we send like a targeted reminder, for example, to that individual, they are much more likely to go back to that schedule if they are in the non-engaging state, or if they are still in that engaging state, they are much more likely to remain in that engaging state if we take that action. But the challenge is we only have a limited number of actions that we can take. We can only intervene on so many individuals. So figuring out who to best intervene on is our challenge. So just for the purpose of illustration, note that I'm giving this example with a relatively simple binary state context. So there's just the S equals 1 is the engaging state and S equals 0 is the non-engaging state. But this kind of problem of restless bandits can also apply to much more broader contexts in which there are many, many states. And what's notable here is, unlike many cases where you might be familiar with Markov decision processes, note that there is an individual MDP representing every individual in this context. So there are n total MDPs, and within within one district, for example, we can imagine that n being very large in like the thousands or tens of thousands or something like that. So this problem gets computationally complex very quickly. So then again, the question is, who should we intervene on within a given week, for example, in order to minimize electricity usage and maximize engagement in this program? So of the N users who are enrolled, we can, within each week, call some subset of them K, but the number K is much smaller than that number N. So broadly, these restless bandits problems are p-space hard for the planning problem alone. So assuming that we have perfect information about the entire setting, so we know the state of every individual because we can see their exact power usage. We know the transition probabilities they have of moving from engaged state to non-engaged state. So it's a really computationally complex problem. But unfortunately, sometimes the transition probabilities will not be known. So for a new user enrolling in this program, or if we're implementing this in a new neighborhood, it's unlikely that we know exactly what the transition probabilities will be like because it's a completely new demographic and they have their own patterns of use. So how now the question is, how can we do this kind of complex planning when there's uncertainty in the environment? And when we're talking about uncertainty for intervention design and planning, there are two key types of uncertainty that we can consider. So one of them is epistemic uncertainty. So this refers to uncertainty of things that we could know but do not know in practice. Um, And then aleatoric uncertainty is uncertainty that is intrinsic to the problem setting, which is inherently noisy and stochastic. So to have an illustration to better understand this, let's imagine that there's some space, and then the x-axis refers to a parameter of interest, and then y is the model that we're trying to build. So here are some data points that we've observed so far. And we can fit a reasonable model to these observed points. So, let's say here's a model that I fit. But there is some uncertainty in this model, and let's look at the two forms of uncertainty here. So epistemic uncertainty indicates things, again, that we could know if we had more data. So here, epistemic uncertainty is demonstrated in the space where we just don't have any prior observations. So if we had collected some data from these parts of the problem space, then we could reasonably fit a model that would continue stretching further to the positive and negative sides. So here we could reduce that uncertainty with the collection of more data. But aleatoric uncertainty, on the other hand, refers to uncertainty that is intrinsic to the problem setting. So as we can see, there's no single model that would perfectly capture this data because there is just inherent noise in the data. So there will always be some error that arises from the noisiness of the problem context. So this is uncertainty that is irreducible. Regardless of how much data we have, regardless of our knowledge of the problem setting, we will not be able to reduce this uncertainty. It just exists. Um, so understanding these two different forms, this tells us that the approaches that we should be taking in order to help overcome uncertainty really should depend on which of these forms has a we're looking at. So for epistemic uncertainty, where there are things that we could know but don't know because we don't have enough data on it, the reasonable answer is to just collect more data. So we can collect more data within those spaces, and broadly, when we're collecting data, oftentimes high stakes context requires learning by doing. So we can't just collect information for free, but rather the act of collecting data will oftentimes require us to expend resources, and that comes at some cost. Specifically, it comes at the cost of potentially taking intervention that would improve our utility, however that is defined. So, for example, in the example of the transition towers, if we don't know whether or not a specific tower is kind of at risk of failure, we'll have to send somebody out there to do an inspection. And doing an inspection means that the trade-off has been we could have instead sent that person to go maintain a tower that we already know is in need of maintenance, for example. But the trade-off is that the tower where we don't know the exact condition could be at risk of kind of like extreme failure. So we don't want it to go for too long, even if we have this kind of like long list of places that need like smaller, like more trivial maintenance, for example, but is less urgent. So this is described as online learning, where there is a trade-off between taking action versus collecting more data. And we refer to that as the exploitation trade-off. So we can either explore areas that we have uncertainty and therefore collect more data and improve our model so that we can have better utility later down the line. Or we can do exploitation of areas that we already know but might not ultimately give us the highest form of utility. Okay. And then in the case of aleatoric uncertainty, where there's just intrinsic noise in the problem setting, what we want to do is quantify, if possible, the amount of noise and then plan around that using robust planning. So if we can characterize that underlying uncertainty, then we can design policies that will be more guaranteed to perform well across that space of uncertainty. So this is a space of robust planning. And then I'll talk here about some work that I've done thinking about addressing both online learning and robust planning. Okay, so we are broadly working in the space of restless bandits. And for the first form of uncertainty, of epistemic uncertainty, there is uncertainty about exactly what the model of the environment looks like. So here, in this example, we don't know the exact transition probabilities of a certain user going from and engaging in like an energy reduction program to not engaging in this program. So we have to estimate these transition probabilities in an online way as we're engaging with them throughout the course of this program. So this framework of online learning is often addressed using what's called multi-armed bandits. And the most simple form of a multi-armed bandit is known as a stochastic bandit. So every action that we can take is referred to by an arm. So we have arms A or B, and we keep track of the reward we've gotten for taking each action. So this circle in the middle refers to the reward that we've achieved uh, in average based on our historical data. But then the confidence interval, this interval refers to our uncertainty about whatever that true reward estimate is. So as you can see, we've observed slightly higher average reward for action B than action A, but its uncertainty interval is smaller. And the common approach for addressing stochastic bandit problems is known as UCB, or upper confidence bound approach. And the key idea behind stochastic bandits is this notion of optimism in the face of uncertainty. So if there's uncertainty about what the underlying reward is, we'll take whatever action has the highest upper confidence bound, regardless of what the average reward is in the observed data, with the idea that we can either um, uh, if we're taking the approach with the highest amount of uncertainty and the highest upper confidence bound, either we have the potential of achieving really high reward, which would be good for our goals, or we have the option to drastically improve our model by reducing our uncertainty so that we can make better decisions in the future. So it's kind of like thinking about that as a form of investment. We might not achieve good reward immediately, but it will enable us later down the line to perform better. So this is a common framework with for online learning. But if we're applying this for restless bandits, now the parameters that we're uncertain of does not directly translate to the reward. So for stochastic bandits, there's uncertainty about the reward of action A and the reward of action B. But now for restless bandits, the things that we have uncertainty over is the transition probabilities. And then the reward comes only after we've transitioned and we've determined which state we're in. So here, there's uncertainty over these parameters Pi and Qi. So we can similarly maintain some kind of estimate of, we have observed so far that Pi is usually 0.7 and Qi is usually 0.4. And then we can maintain confidence intervals over that. But the key challenge is that if we apply a similar approach of using this principle of optimism in the face of uncertainty, the uncertainty is not over our reward estimates directly, but it's instead over a different parameter of the model that's not directly translating to a reward. So here, the upper confidence bound of these transition probability confidence intervals does not directly translate to an optimistic notion of reward. Um, so we have to think about how do we do planning in this context instead. So to just bring out some notation, we have a fairly standard notation for Markov decision processes, which is some state, a set of actions, a reward function, and transition probabilities. And here, notably, we have different transition probabilities for each arm, for each user in the program, for each transition tower separately, because they are independent. And then the true transition probabilities are unknown here. So we'll refer to those true transition probabilities as P star. And our goal is to learn these transition probabilities so that we can um, take the best action later down the line. And our objective is to maximize the total discounted reward. So this is, again, very standard with reinforcement learning and solving Markov decision process problems. So this is just referring to we want to take some policy pi that maximizes our expected reward, referred to as reward R of state I, AI. So for each arm, our reward is a function of what state is that arm in. So is this user engaged or not engaged in the electricity reduction program? And we have some discount factor that enables us to sum up reward over potentially infinitely long time horizon. And then our action is to pick some of these n different possibilities, intervene on some subset k of these overall actions. So again, here we're looking at a fairly simple action space, which is just a binary action, so we can intervene or not intervene on each setting. But again, this framework will scale and translate to more complex action spaces as well. So a common approach with restless bandits is to apply Lagrangian relaxation to make this problem tractable. So instead of directly addressing this constraint, where we have to satisfy the budget and intervene on at most k, we apply relaxation to enable us to potentially identify actions that will exceed our budget constraint, but we penalize the amount that we're exceeding the budget constraint by some parameter lambda. And what this enables us to do is define a heuristic policy, which is known as the Whittle index, which enables us to translate these instead of having to do planning throughout the entire problem space of determining some combinatorial action of picking k choose n of all of the possible decisions, instead we can evaluate the benefit of acting on each arm individually. So here the Whittle index is referred to as the smallest penalty that we define, where taking an action on an arm is equally as good as not acting on that arm. So here the Whittle index is referred to as MI, that makes it so that acting A equals 1 and not acting A equals 0 are equivalent. And then the Whittle index policy is to just take actions on all the arms with a Whittle index higher than some penalty threshold. And critically, this enables us to break down the problem setting so we don't have to evaluate the benefit of one action across the entire space, but instead we can evaluate the relative benefit of acting on each arm individually and then translate that into an overall policy. So the way we do that translation is we can plot what all the Whittle indices are for each arm. So this is saying how beneficial will it be for me to intervene on user A or user B or user C. And the lambda term, that the penalty threshold that we learned, gives us some value. And then the Whittle index policy is to just intervene on all arms that have a penalty higher than this lambda value. So that's a simple way of translating this problem into something more computationally tractable. But now we want to bring this problem to an online learning setting. So to better estimate transition probabilities, we can look at the space of uncertainty. So let's say that there's three parameters that we're uncertain over, P1, P2, and P3. And we can maintain some estimates, just as we did, that's just as we demonstrated, of the average value of these transition probabilities. So I've denoted in blue, this dot refers to the average value of each one of these transition probabilities based on our observation so far. But because there's noise in the data, we can also construct a confidence interval of where the total bounding box of the space that we think these transition probabilities will lie in with high probability. So that gives us some box of uncertainty, and we're very confident that the true transition probabilities, the true parameters of the problem space will lie somewhere within this box. We don't know exactly what it would be. And then the standard approach for optimism in the face of uncertainty is to just take the upper confidence bound, which will correspond to this upper right corner of this box. But again, as we've noted, maximizing transition probabilities here is not the same as maximizing reward. So instead, we want to understand some notion of optimism in the transition probabilities that will not just be the uppermost value, but instead lead to the highest potential value starting from whatever our current state is, SI. And the approach that we introduce for solving for this notion of optimistic transition probability comes from mathematical programming. So we define a mixed integer program where the objective is to maximize the potential value from being the state S. And we include as constraints the Bellman equation, which is a common formulation in reinforcement learning to enable us to estimate what is not just the immediate reward of taking one action, but what is the long-term reward if we have repeated actions over time across many, many time steps. So this is just writing out the Bellman equation, where the Bellman equation gives us the estimated Q value, which is the benefit of taking a specific action from the current state. And then the value function is just defined as whatever highest Q value there is for a specific state. So the value function just looks at all the Q values with the different actions that we could take, and then just finds the maximum value of that. So that's how we define the maximum potential value here. And then the decision variables we'll note are V, so the value function for each state, the Q function for each state in action, and then all these transition probabilities, PI, that we have constrained to sitting within the box that we just described earlier. That comes from our historical observations where we form that confidence interval. And then when we solve for this mixed integer program, what we have is that whatever values are assigned to these transition probabilities PI, these then become the optimistic transition probabilities that will lead to the highest value. So from here, we can take this transition probability value and then use that to solve for the highest, the optimal Whittle index for each arm, and then we can use that to construct an overall policy to determine which individual should we intervene on within a given week. And then we also, in our paper, provide a heuristic approach that will take a relaxation of this problem, but is computationally much faster. And to just share a little bit of the results, we show in our paper that this online learning for Restless Bandits approach that we provide achieves the following regret bound, where in online learning, we want regret to be as low as possible, and we really care about the time horizon. So we have a time horizon H and T total episodes, so T repeated settings where we're seeing like a new slate of users, for example. And by focusing on the time horizon and number of episodes, which are, again, the dominating parameters, our approach achieves the following regret bound of O of H of root T log T, which is a frequentist regret bounds that provides this guarantee for every every possible instantiation of this problem setting, where the reward and uncertainty can fall across a very large range with no assumptions over exactly what the uncertainty would look like. And this contrasts to an existing approach of Bayesian regret guarantees for Restless Bandits, where the Bayesian regret bound requires a prior that is set over the uncertainty space in advance. So that requires that people will first have some understanding of what the uncertainty will look like. And we are able to match their regret bound, but reducing this requirement of having prior knowledge over what the uncertainty is, which is just enables us to be flexible for a larger set of problems. Okay. We also have results evaluating the empirical performance of our approach. So our algorithm is shown in red, and again, the regret lower is better. So we compare against these various baselines. And then in yellow is a heuristic approach um, that uses a relaxation of the problem, but is able to achieve about a six-fold speed up compared to this more exact approach. So we show that we can achieve much better computational and efficiency gains with relatively low trade-off in performance. And we also have follow-up work that appeared at AAAI this year that's bringing context to this problem space. So moving to the space of contextual restless bandits. And a challenge is that with the approach that we've described, it's a little bit hard to scale because we have to estimate every transition probability individually. And for the example that we've been considering so far of a binary state, binary action problem, there are four transition probabilities for every arm of the restless bandit, and there's n different arms of this restless bandit. So this requires us to estimate 4 times n total transition probabilities, which scales as our problem size scales. And again, we've discussed that we can easily have settings where we have thousands or tens of thousands of individuals that we have to do planning over. So this problem would not scale very well. But instead, we can apply a Bayesian hierarchical model that enables us to take the demographic features of different individuals enrolled in the smart metering program. And then instead of trying to estimate the transition probabilities for every individual, we'll estimate them, we'll instead estimate the relationship between some parameters on those demographic features. So instead, we're leveraging context from the demographic data, and then the size of our problem is now only with respect to the number of parameters on those demographic features and is now independent of n. So if we have 10 demographic features and then let's say some model where there's 2 parameters per model, now we have a fixed 20 number of parameters that we have to estimate, which is now independent of n. So we can scale to much larger problem sizes. Okay, so that was looking at epistemic uncertainty. And then the next part is thinking about how to overcome aleatoric uncertainty. And this is doing robust planning over interval uncertainty. So we're still looking at this example of restless bandits. And we can look at what is the probability of some user enrolled in our program of staying engaged without us intervening on them. So we might have some uncertainty interval for each of them. And the existing approaches for restless bandits is to just take the center of this interval. So here the two users would be treated the same. But instead, if we looked at the worst case scenarios for these users, it's much worse for user one because it's much they're much less likely of staying engaged. So this is their likelihood of dropping out of this program. And what this means is that this user might have high electricity bills. They're less likely to be intervened on, even though they should receive this intervention more than user two. So only by looking at the uncertainty interval and doing robust planning and recognizing the need of user one is higher than the need of user two, would we be able to recognize this? So the question is, how do we apply this form of robust planning for restless bandits? And for a more broad case where the uncertainty intervals are not so interpretable, we introduce a notion of robust planning called minimax regret, which compares to a standard notion of robust planning for reinforcement learning known as maximizing the minimum reward. And let me show you the difference between the two. So let's now think about a problem setting where we have only one parameter that we're uncertain over. So let's call this z. And z can take on one of three values, so 0.12, 0.17, and 0.23. And for each context, so we can evaluate what is the best possible policy that I can take for this problem. And then this gives me some pi star. And then I can also look at what is the worst possible policy that I can take for each context. And then the space in between the best possible policy and the worst possible policy is this gap in decision quality. So this really refers to the space over which we have control. And then if we're now considering a single policy that we apply to all settings, so again, we don't know which one of these three settings it will be, and we're just picking some policy and then trying to apply it all throughout. The case where our policy pi1 achieves the minimum reward is this first case. So the common approaches of robust planning for maximizing the minimum reward will therefore focus on this first context and try to change our policy to do a little bit better. But notice that our ceiling is very low. So we can only do a very incremental improvement. And beyond that, it's just infeasible to improve further. But instead, if we look at regret, which is really evaluating how well our policy is doing compared to the best optimal policy, then that space of regret is maximal in the third context instead. And it's very little in that first context where, again, the ceiling is very low, so there's not much improvement that we can get. So the objective of minimizing the maximum regret will instead focus on this third case, which is really thinking about what is the autonomy we have in this problem? What is our opportunity to improve? And I think of this as a much less conservative notion of uncertainty planning. And I think it's just a more useful heuristic, especially for these types of complex problems. So what we want to think about now is how to do robust planning with this new objective of minimizing the maximum regret, but I'll show why this is a very hard objective to solve for. So this is just writing out our objective. So we want to find some policy pi that will minimize our maximum regret. And regret is over the uncertain parameters. So we're kind of bundling up all the parameters that we have uncertainty over as z. And then regret is defined as whatever the optimal policy would be for that z value compared to the reward that we're getting for that current z value. And our policy here is some continuous sequential mapping of states to actions. So this is exponentially large and continuous. And then these uncertain parameters z are continuous values. That's also a very large uncertainty space. And then the optimal policy pi star has to be solved for every time that we update z. So with a little change in z, then the optimal policy pi star will subsequently change. So there's really an underlying maximization term in here as well. So it's really a min max max problem, which is and each component of this, the pi, the z, the pi star, are all fairly complex. So this is a really large search space and therefore fairly intractable. Our approach is enabling robust planning with this minimax regret objective by making this objective more tractable. So to more feasibly search within this very large space of uncertainty, we set up this problem as a two-player zero-sum game where there's a planner that's trying to, given some fixed environment setting z, find the optimal policy pi to minimize regret and therefore maximize reward. And then we have kind of an adversary that we refer to as nature that's setting these environment parameters that will, for some given policy pi, find a worst case environment setting for us. So it will constantly, similar to curriculum learning, it will constantly give us a harder environment that will challenge us more and more and cause us to achieve higher regret, which will force us to then learn a new policy pi that is better for that harder problem instance. And the approach known as double oracle enables us to go back and forth between this planner and nature and iteratively um, search through this very large uncertainty space so that we can eventually converge to an optimal policy, which we show that this convergence will occur within a finite number of time steps. And then to just apply this um, problem of minimizing the maximum regret for restless bandits. This is separate from the environmental context, but along the lines of some public health work that I've done on maternal mortality prevention in India. So we have similar to this context of having individuals in like a smart metering program be engaging or not engaging. We have pregnant women who are engaging or not engaging in some preventative care program. But it's a very large scale program, so we'll have up to 20,000 women enrolled. And to enable planning with restless bandits at scale, the first step is to cluster these individuals with similar demographic features into groups. But because of this clustering approach, this leads to intrinsic aleatoric uncertainty in the model. So within each cluster, even though the mothers might kind of be similar, their true transition probabilities will have natural variation across them. So this is variation that we cannot reduce regardless of how much more data we have, because within each cluster, there will just be natural variance. So this is aleatoric uncertainty, which is irreducible in the model. And then now what we can do is we can take these clusters, take our historical data, and estimate uncertainty intervals for the transition probabilities within each group. And then we can take the approach that we've just introduced for applying double oracle to this minimax regret planning process and do that planning at the group level. And then we can translate those estimated group level Whittle indexes into some arm level policy. So translating the group level estimates to the individual. And we have a theorem in our paper that shows that the worst case regret of planning over groups is the same as the worst case regret of planning over individual arms. And really what this tells us is that doing planning at the group level does not incur additional regret, with the assumption that all arms in a group have the same uncertainty intervals, but then the true values for every individual can be any value within, as long as it sits within the bounds that we defined. And again, we evaluate our approach on real data from the maternal health context here, showing that our regret of this group's policy is indeed lower than existing baselines. Um, so just in the interest of time, sorry, let me just move towards the end. Skipping over 2 slides. Um, oops, sorry. Here we go. Yeah, so just to close off, environmental challenges very often involve repeated interactions in these kind of high stakes contexts with incomplete data. And this uncertainty and the messiness of the data can manifest as either epistemic or aleatoric uncertainty. And if we want to design more effective interventions, we can use online learning to reduce uncertainty when it's reducible, when it's epistemic, or we can use robust planning to work within uncertainty that is irreducible or aleatoric. And then there's other considerations that we have to consider, like planning at scale and addressing real-world constraints. So this is just an overview of the papers that I discussed here. And please feel free to find me online. So linking to my website on Twitter or Blue Sky. And I'm currently growing up my research group at Columbia that is focused on decision making under uncertainty for sustainability and planetary health applications, with a big focus on biodiversity conservation. So always happy to talk more about that. And excited to jump into discussion. Thank you so much.